Let's continue our study of thermodynamic processes that take place in open system by looking at diffusers. Superheated water vapor is flowing through a diffuser operating under steady state conditions. The steam exits this diffuser as a saturated vapor with negligible velocity. Heat transfer from the steam to the environment is 20 BTUs per pound mass. There's no significant change in potential energy. Inlet conditions are 300 degrees Fahrenheit and 14.7 psia. Inlet velocity is 500 feet per second, and we wish to determine the exit pressure. So let's lay out a storyboard for this problem, beginning with a schematic. A diffuser is a device with expanding a cross-sectional area in the direction of flow. And in this case, we have steam flowing through the diffuser. And we'll draw our boundary around the steam that is inside the diffuser, so that our system is only the steam molecules and does not include the metal diffuser. Now, in a diffuser, the velocity at the exit is less than at the inlet, but the pressure at the exit is greater than the pressure at the inlet. And so gases flowing through a diffuser are undergoing a compression device. The data given in the problem statement is that the initial temperature is 300 degrees Fahrenheit. The initial pressure is 14.7 psia. The initial velocity is 500 feet per second. At the exit, we know only that the steam has become a saturated vapor with an insignificant velocity. We'll call it 0. We were also given that for this process 1,2, the heat transfer is described as a minus 20 BTUs per pound mass. Negative because the energy is flowing from the system to its surroundings. Let's draw a property diagram, a TV diagram of this process. We know that state 1 was given as superheated steam, and it had a pressure of 14.7 psi, and its temperature was 300 degrees Fahrenheit. So we'll plot state 1 here. State 2 is at an unknown pressure, but we will assume that the pressure P2 is greater than the pressure of P1, so this would be the constant pressure line P2. We also know that state 2 is a saturated vapor, so it's going to be sitting right on top of the saturated vapor line, which is the right side of the vapor dome. So we can conclude that in this compression process, that the specific volume at state 1 is greater than the specific volume at state 2. We'll model this as an open system operating at steady state. We know that no power is put out during this process because the diffuser has no mechanism for doing work, and that the potential energy change is 0. And we wish to find the pressure at the exit. So now let's write an energy balance for this problem, and then for convenience, divide it by the mass flow rate. So we have our typical energy balance. We've eliminated the work term and the potential energy term, and divide by the mass flow rate. We get 0 is equal to Q dot over M dot plus H1 minus H2 plus V1 squared over 2, because V2 squared is also 0. And we're left with 0 is equal to Q plus H1 minus H2 plus V1 squared over 2. Well, we don't know the enthalpy at either state yet, but we can solve for it at state 2. It's just H2 is equal to H1 plus Q plus V1 squared over 2. And we can find H1 in the superheat tables. It's superheated at 300 degrees Fahrenheit at 14.7 psia. We can get that value for state 1 enthalpy directly from the table. And now we can solve for the enthalpy at state 2. It's just the enthalpy at state 1 plus Q, which is a minus 20 BTUs per pound mass, plus V1 squared, so that's 500 feet per second quantity squared, divided by 2. Now, we have units of feet squared per second squared, and we need that in units of basic energy, which would be a foot-pounds force. Well, how do we convert feet squared per second squared to foot-pounds force? As we did in previous lessons, we divide by the constant g sub c, which has a value of 32.174 foot-pounds mass per pound force second squared. Now, if you're not yet familiar with g sub c and this unit conversion, then go back to my very first lesson in this series and learn how g sub c was developed. Now that I've got the kinetic energy change in units of foot-pounds force, I'm going to convert foot-pounds force to BTUs. And I get H2 is 1178 BTUs per pound mass. So now state 2 is fully defined by two independent properties. One is its enthalpy, and the other is that it's a saturated vapor. So I can go into the water saturation table and look for a value of H sub G is 1178 BTUs per pound mass. Fortunately, I find it without having to interpolate, and I get a value of P2 is equal to 60.0 psia.